In this video, we're going to look at isotopes and how this relates to atomic mass. So all neutral atoms of the same element contain the same number of protons and therefore the same number of electrons. However, the number of neutrons can vary, and this leads to isotopes. So isotopes are defined as atoms of an element that have the same number of protons but different number of neutrons. And because they have a different number of neutrons, it means that they differ in mass. So an example is carbon. Carbon has 3 isotopes. There's carbon-12, which has 12 neutrons. So if we were writing out its notation, it would be 6 and 12. It also has carbon-13, which would be 13 and 6, and carbon-14, which would be 14 and 6. So these are 3 different isotopes of carbon. Now, some isotopes are radioactive, but not all isotopes are radioactive. So what is radioactivity? It results from unstable nuclei decaying. And when they decay, they release energy and they release some subatomic particles. It might be a proton or a neutron that it releases. One interesting fact is that any isotope of uranium is always unstable, so they are all radioactive. And these unstable isotopes are known as radioisotopes. If we go back to carbon then, carbon-14 is a radioisotope of carbon. And you can use carbon-14 to do carbon dating, to find out how old something is based on how much that carbon has decayed over time. But carbon-12 and carbon-13 are not radioactive, only carbon-14. Some other examples is hydrogen-3, or we refer to it as tritium. And this is a radioisotope that's used as self-powered lighting. So things such as watches and exit signs actually makes use of tritium. Another example would be phosphorus-32. And this one's used quite a bit in many aspects of science. So it can be used to identify malignant tumors because cancer cells accumulate more phosphorus than normal cells. It's used in many different types of experiments in science. So it's a very, very useful radioactive isotope of phosphorus. Now, because isotopes have different masses, and each element on the periodic table has a certain number of isotopes, whether it just be one isotope or 2 or 3, it leads to atomic masses that are written on the periodic table that are averages of the masses of all of the elements' isotopes. And what it does is it takes into account the abundance of each. And so these average atomic masses are what you see on the periodic table. If you look at carbon, carbon's average atomic mass is 12.01. And that's because carbon is made up of isotopes of carbon-12, 13, and 14. And so each of those isotopes' mass is 12, 13, or 14 respectively. And if you take into the abundance of each and add them all up and average it, it gives you an average atomic mass of 12.01. So what this means is that most of carbon's isotopes are probably carbon-12, and very few are 13 and 14. Now, in order to calculate the average atomic mass, what you would do is you would take the atomic mass of each of your isotopes and multiply it by the relative abundance. This is always given as a percentage, but you're going to want to put it into decimal form in this formula. And so you're going to take each of the atomic masses of each of your isotopes, multiply it by the relative abundance, and then you add them all together. So this formula is given for just 2 isotopes, but if you had a third one, you'd do the same and multiply it by its percentage here. If you had a fourth one, you'd do the same for that one as well, and so on. Let's look at an example then. In this example, silver exists naturally as 2 isotopes. Silver 107, so that means its atomic mass is 107 U, or AMU, and silver 109, so its atomic mass is 109 U. Silver 107 is 51.8%, and silver 109 is 48.2%. So those are the relative abundances. Now it's asking us to find the average atomic mass. So the average atomic mass is going to be equal to the first isotope, which has a mass of 107 U, or AMU, and we're going to multiply that by its relative abundance as a decimal. So as a decimal, it's going to be 0.518. And then we're going to add that to our second isotope, which has a mass of 109 U, and multiply that by its relative abundance, so 0.482. Now I'll just do this in a couple of steps. So if we do 107 times 0.518, that gives us 55.426, and we'll add that to 109 times 0.482, which is 52.538. Adding those two together then gives us 107.964 U. We're not going to talk about how to round off these yet, but what I would like you to do as your answers is always keep 2 decimal places. So the answer for this, the final answer, would be 107.96 U. You can also write AMU, that's okay. Okay, so I'm going to leave you with this second example to try on your own. And what we will do is we'll take this up together in an online tutorial later on. In this example, rubidium consists of rubidium 85 and rubidium 87 and has an average atomic mass of 85.4678, and I'll put in the units here, U. Calculate the relative percentages of these 2 isotopes. So this question is a little bit different than the last one. I will give you a hint in that you're going to end up with 2 equations and 2 unknowns. And so you're going to have to solve 2 equations, 2 unknowns. Give it a try, and we'll take it up together later on.